Welcome student PCH for it 02 unit 2 1 group and 2 group C X disconnection. I am Dr. Devangar Pandya from Department of Chemistry St. Xavier's College Autonomous Ahmedabad. Well, let's begin our today's lecture with 1 group CC disconnection. Before I start 1 group CC disconnection, let me arrange the pointer. Yes. The disconnection in which we need to recognize only one functional group to know the position of disconnection are known as one group disconnections. These are fundamental to synthesis design. The label CX indicates that we disconnect a bond joining from carbon to heteroatom. Yeah, X is any heteroatom, maybe nitrogen, oxygen, sulfur. We have already discussed one group, that is CN or CO or CS bond disconnections in the case of amide, amines, ethers, ester and sulfides. Similarly, in aromatic compound, one group CX disconnection almost always involves the bond joining aromatic ring to the rest of the molecule. Now, the corresponding reactions are mostly ionic and involve nucleophilic heteroatoms, as in alcohol, that is ROH, amines, that is RNH2, and thiols, that is RSH. The disconnection will therefore give a cationic synthon, that is structure 1. The reagent for structure 1 will usually have a good leaving group attached to alkyl group, that is structure 2. In other words, the reaction is substitution of some kind and the reagents will be alkyl halides, acid chlorides, etc. So here there is RX, alkyl and heteroatom, carbon and heteroatom. We have put a wiggly line over here. In the inclined arrow, carbon and heteroatom disconnection would be there. Heteroatom because it is more electronegative compared to carbon, carrying negative charge in the synthon, and carbon contain positive charge, that is nucleophilic carbon, and that can be converted into synthetic equivalent using this substituent group that may be bromide, tosyl oxide, etc. Now, carbonyl derivative, that is RC double bond OX, and retrosynthetic analysis of ester. Acid derivatives are usually or maybe we can say very easy to disconnect, and hence we almost always choose the carbonyl group and the heteroatom for first disconnection. So here you can see the carbonyl group is there and heteroatom. We put wiggly line, something is missing. It is completely wiggly line over here. On inclined arrow, carbon heteroatom disconnection would be there, and that will going to bring this heteroatom electrically negatively charged and carbon positively charged synthon, and that synthon can be converted to synthetic equivalent by attaching proper element or group to it, and that way we will going to get our synthon converted into synthetic equivalent. The ester, that is structure 3, is used both as an insect repellent and as a solvent in perfumery products. Its retrosynthetic analysis and design synthesis we can see here. This is the retrosynthetic analysis. Here you can see the carbonyl group and then carbon and then heteroelement, that is oxygen. So we do not need to find out another site for disconnection. Our site is pre-decided and that is this. So we put wiggly line over here in the structure 3. So that is CO disconnection and it's going to form ester on the synthesis. So now we have these two synthetic equivalent. Now design synthesis of ester. The synthesis can be carried out in several ways using acid chloride, acid anhydride, etc. Perhaps the acid chloride route using chloride is the easiest with pyridine as catalyst and solvent. The acid chloride are often used because they are most reactive of all acid derivatives and because they can be made from acid themselves and PCl5 or thionyl chloride. So here we have our synthon that is treated with this acid chloride in presence of pyridine. We're going to get our target molecules, that is ester structure 3. Now alcohol, ether, alkyl halide and sulfide, one group CX disconnection. In these aliphatic compounds that gives a nucleophiles, that is X, that is heteroatom and H, and an electrophile, that is carbon species, usually represented as an alkyl halide or tosylate or mesylate, that is methane sulfonate, that is represented as OMS, etc. All these compounds can be made from alcohols, and alcohols can be made by C-C bond formation. We shall treat alcohol as the central functional group. The retrosynthetic analysis of alcohol, ether, alkyl halide and sulfides can be shown over here. Here we have this X if we are going to take as a heteroelement. So CX, that is carbon and heteroelement disconnection, would be there and going to give this 2 synthon, and that it can be converted into this kind of synthetic equivalent. Now the desired synthesis of alcohol, ether, alkyl halide and sulfide. So we have this RBr or R-tosyl oxide or mesylate that is treated with our this synthetic equivalent, that is XO. X is a heteroelement, will going to gives us RX, that is our alkyl halide. Alcohol is there treating either tosyl chloride or mesylate or treated with HBr in presence of PBr3. We're going to get these 3 reagents. Now aliphatic compound derived from alcohol, we can treat with a base or either this, then this. Ether is going to be formed, sulfide is going to be formed using this reagent, thiol is going to be formed, halide is going to be formed from this, converting alcohol to RX, alkyl halide. We're going to get this new derivative, nucleophile derivative as well. Now ethers and sulfides. We often choose our first disconnection because of the reactivity or lack of it of one side of the target molecule. The oxygen atom in the compound 4 has a reactive side, that is methyl group, and that can be done by SN2, and the unreactive, that is aryl side, so disconnection is easy. It should be on the reactive methyl side. The retrosynthetic analysis is given over here. So instead of aryl side, we can put wiggly line to methyl side, as already we have shown that methyl has a reactive side. So we are going to put disconnection over here. It is CO disconnection for the ether, and we're going to get this synthetic equivalent and synthon. Now design synthesis. So here you can see our starting reagent treated with methyl sulfate in presence of NaOH. We're going to get our target molecule structure for, that is ether. Now the Gardenia perfume compound, that is Gardenia perfume compound structure 5, can be disconnected on the ether side as both involves primary alkyl halides. The benzyl halide is more reactive, but the deciding point in favor of route B is that route A might lead to elimination. So we select route B. So here is the retrosynthetic analysis and disconnection. We have these 2 routes. but in this we will going to be more reactive, yet we are going to decide route A over here. So when we would disconnect from route A, we're going to get these two synthetic equivalent, and if we are going to use route B, so it's going to gives our ether, not ester, is by mistake written as an ester, it's ether. We're going to get these two synthetic equivalent. Now design synthesis, and as already we said, our design synthesis is more using this route B, which is more favorable. So we're going to take this alcoholic group treated in presence of base, we're going to get this intermediate, and then treating with phenyl benzyl chloride, we're going to get our target molecule. Now the same principle applied to sulfide, that is RSR synthesis. The reaction is even easier by SN2, as thiols ionize at a lower pK than alcohol. Anions Rs minus is softer than Ro minus, and thus more nucleophilic towards sp3 carbon atom. So here we're going to put wiggly line over here. It is CS disconnection, is going to form sulfide, and this synthetic equivalent and synthon is going to be obtained. The acaricide chlorbenzide, that is structure 6, used to kill mites and ticks, is disconnected on alkyl side rather than the aryl side. As you know, alkyl side is more reactive compared to aryl side. Retrosynthetic analysis would be here. We're going to put a wiggly line over here to disconnect this. It is missing. You need to understand that wiggly line is there, and whenever you show disconnection or retrosynthetic analysis, you need to put wiggly line over here. I just forgot it to put it here. You need to put it over here. That is CS disconnection, and it's going to gives us this synthetic equivalent and synthon. Now the design synthesis, that is our two synthetic equivalent treated with sodium ethoxide in presence of ethanol, we're going to get our target molecule, which is used to kill ticks and tags. Now two group CX disconnection, another topic of our today's lecture. All the disconnections we have used so far have been one group disconnection. We have recognized a single functional group, and the disconnection corresponds to a reliable reaction to make the functional group. The disconnection in which we use one functional group to help disconnect another elsewhere in the molecule are known as two-group disconnections. Use two-group disconnection wherever possible because they are more efficient disconnections than one-group disconnection in reducing the complexity of the target molecule. One dysfunctionalized compound we are taking for the example. Let us take the example of acetals or ketols, that is structure 7. In this compound, we can use one oxygen atom to help disconnect the other, as shown here in this example. You can see this compound would be there. So on disconnecting one, we're going to get this, and then again we're going to disconnect it from here. We're going to get this synthetic equivalent. Now both carbon oxygen bonds have been disconnected, and we can label the operation 1,1-dix to so that it is a two-group dix disconnection. We have also numbered the compound, numbered the carbon atoms pairing the functional group to show the relationship. Here the numbers 1, 1 dash indicates both the functional groups are attached to the same carbon atom. Now let us take the example of retrosynthetic analysis of acetyl, that is structure 8, involving two group DIX disconnection. Here the retrosynthetic analysis is given, and you can see from carbon and hetero element two wiggly line we have put over here in the target molecule. So it is 1,1 DIX acetyl, and we are going to get this benzaldehyde and this methanol 2 mole. Now the synthesis involves these two in presence of acidic condition. We are going to get our target molecule. Acetals are the example of a general type of molecules, that is structure 9, in which two heteroatoms are both joined to the same carbon atom. This carbon is at the oxidation level of a carbonyl group, and the molecule is made from a carbonyl compound and two nucleophiles. Here you can see the example. On disconnecting these two heteroatom, we are going to get this synthetic equivalent and this synthetic equivalent as well. If one heteroatom is present as an hydroxide group, then only one nucleophile is involved, and the molecules such as cyanohydrin, that is structure 10, are obviously made from carbonyl compound and hydrogen cyanide. Let us design the synthesis of the compound, that is structure 11, and that can be done in a retrosynthetic way like this. This will roll up over here. Cyanide is going to be disconnected. We're going to get these two synthons, and then again the disconnection of this will going to bring these two synthons, carbonyl, synthetic equivalent carbonyl and hydrogen cyanide. Now this is another retrosynthetic analysis where you can see target molecule 11 is there, and hence we do not have a direct disconnection of amine or direct any reaction in our mind where we can attach amine group. So instead of doing disconnection over here, we're going to do functional group interconversion, because on reduction we're going to get this one. So on doing functional group interconversion, instead of this methylamine we're going to get the cyanide group over here, and then we're going to put 1,1-dix, then here and here we're going to get cyclohexane and HCN as a synthetic equivalent. Now this in the synthesis, cyclohexanone treating with potassium cyanide in presence of any acid, we're going to get this hydroxide derivative, and on reduction we're going to get our target molecule, that is structure 11. Now 1,2-difunctional compound, and we are going to synthesize alcohol in it. Compound with heteroatoms on adjacent carbon atoms, that is structure 12 and structure 13, are most helpful, considered as derivative of alcohols. Disconnection gave the synthon, that is structure 14, and the reagent for which is the epoxide, that is structure 15. The compound you would get if you tried to make structure 14 itself. Here it is the retrosynthetic analysis. We have these two compound, two ester is there, where one terminal is nucleophile, will perform functional group interconversion, and instead of this estery group, we're going to put hydroxide group. This hydroxyl group attached with the carbon, that is number 1, then second carbon, that is number 2, and then after we are going to put the wiggly line. So it is known as 1,2-difunctional group, that is 1,2-dix, and we're going to get this synthon and reagents. This is converted into synthetic equivalent epoxide. Now epoxide is treated with this nucleoside, that nucleophilic reagent that you can take among these three, and it's going to gives us this hydroxide derivative, and then treated with either acid chloride carboxylic group or treated with chloride, we're going to get these two, and here we're going to get our target molecule, structure 12 or 13. Now carbonyl compound, at the carbonyl oxidation level, another synthon is needed for 1,2-dix disconnection. Just as epoxide are useful reagent for this synthon, we're going to get this is converted into either epoxide. Alpha halocarbonyl compound are useful reagent for the carbonyl synthon as well. We can consider disconnection to this synthon to be a two-group disconnection, because the alpha halocarbonyl equivalent easily made by halogenation of a ketone, ester, or carboxylic acid, and the carbonyl group adjacent to the halogen makes them extremely reactive electrophiles. The herbicide 2,4 has an obvious disconnection by this approach. Yeah, 2,4-D, that is our herbicide, and here we have given the retrosynthetic analysis. So carbon oxygen disconnection would be there. It is 1,2-diox. We're going to get this synthetic equivalent. Then this dichloro-derivative treated with NOH followed by this acid chloride. We're going to get this target molecule. The alpha halocarbonyl compounds are reactive enough to be considered as an alternate disconnection of certain ester. We're going to give you the example of retrosynthetic analysis and synthesis. Here, carbon oxygen 1,2-diox. We're going to get this to synthetic equivalent or synthon, and then we're going to take one of the synthetic equivalent, that is dibromo derivative, treated with carboxylic acid followed by sodium bicarbonate. We're going to get our target molecule. The reaction is simple to carry out and is a way of making crystalline derivative of liquid carboxylic acids for purification, identification, and protection. 1,3-diox functionalized group in 1,2 disconnection. This is going to be the last example. Alpha beta unsaturated carbonyl compound undergo conjugate addition, that is Michael reaction, as you can see in the Michael acceptor. We're going to get this, and this is our target molecule, that is structure 16. The two group 1,3 disconnections are therefore possible, that is structure 16, because they correspond to this forward reaction. This Michael acceptor have an electrophilic site, you can see over here, 2 atoms away from the carbonyl groups, and are therefore the reagent corresponding to the synthon 17. So here you can see this 1,3-diox, 1 carbon second and 3, and then here we are going to put this connection. So the positive charge would be there, and the synthetic equivalent would be our Michael acceptor type of reagent. This type of reaction is available only when the alkene is conjugated to an electron withdrawing group. Usually carbonyl, but it can also be nitro or cyano, etc. This disconnection is available only at the carbonyl oxidation level. For example, we can do a 2 group, that is 1,3 disconnection on the following sulfide. Here the retrosynthetic analysis would be there. We put a wiggly line over here, 1,3-diox. We're going to get this synthetic equivalent or synthon. It can be converted into this reagent, Michael addition kind of reagent. We're going to use it and we'll get the target molecule. Let us take another example of amine, that is structure 18. There is a 1,3 relation between the amine and ketone functional groups, and 1,3 disconnection take us back to piperidine and an unsaturated ketone. Other retrosynthetic analysis is given. We put wiggly line over here. CN disconnection, 1,3 disconnection would be there. We're going to give us this two synthetic equivalent and synthon, and it converted into this reagent, Michael addition type reagent, and then the reaction is carried out between these two. We're going to get our target molecule, structure 18. The use of these beta haloketones as equivalent for the above synthon is not suitable because they are hard to prepare and highly unstable and undergo rapid E1CB elimination. That is the limitation of this synthesis. Well, that is enough from my end. Thank you very much for paying attention to this video lecture. Keep asking questions. As you know, asking question is a beautiful way to get knowledge. Thank you.